work. Good evening, good afternoon. We're going to start our third week today, and we're going to continue on in the end of Chapter 2 with the Fourier analysis and modeling. A fair amount of details in that I want to finally slow down a bit and be able to actually get you prepared to work the problems. If we get a chance to move into Chapter 3, which is the Z-transform, we'll do that. I'm prepared to get rolling on that too. I think the problems keep you fairly busy, but you have lots of alternatives. The classical solution technique won't have to be used. You can use Fourier methods if you want to. I don't want you jumping up and using the Z-transform. That's pretty much a no-no right now. We're going to have different types of problems we'll be using on the Z-transform, but this chapter, the problems involve Fourier, and Fourier analysis can be used to go back and forth from time and frequency, and of course difference equations, solutions, some other little things I'm going to try. I've got on my iPad here, I've got the solutions to try to remind me of some things I want to mention for you to make note of in the homeworks as you're working them. What have I posted that's new? I've just posted the hints, and I'm hoping that everybody saw the password on the channel. Now that I'm recording, I don't want to broadcast it. The integrity issue for me is I've got solutions to homework problems that are in the book used around the world, so I don't want to share unnecessary information so everybody can have it secure. But I can tell you at break time. But it is on the Modern DSP channel. So of the three of you, if you now got it, you can get into the files. We'll keep using that all the way through when I post solutions to homeworks, the old exams. It'll all be through that same password. So we'll just keep using it. Okay, I'm going to keep grabbing my mouse, which I was hoping maybe would start working, but it hasn't. The mouse is working, but it's not working through my little wireless transmitter over here. So we're going to go back and just quickly get through the stuff we did last week a little bit, the frequency domain representation. One of the things I'm going to feature, though, out of Python is I'm going to just show you how to get Pi Audio Helper configured, and we'll do a Jupyter Notebook example of real-time audio DSP, because that's something I'll eventually want you to have for working the first project. So we came through this last time. We have this definition of the frequency response in terms of the impulse response. So we're intimately tied to that to go between time domain and frequency domain on the impulse response. And shortly here I'll be expanding that to the signals themselves, the x of n to x of e to the j omega to y of n to y of e to the j omega. And you might even already be questioning, why do we have, in the notation, why don't we just say h of omega rather than h of e to the j omega? And my sense of why we do that is because everything in the discrete time domain, the frequency spectra and the frequency responses are always periodic. And by putting e to the j omega, we know that we have a periodic function. E to the j omega means that omega is a modulo 2 pi function, and that gets emphasized here in a moment as well. That's just the notation. And then the other thing convenient about this when we come up to the next chapter, we're going to have this complex variable z from the Z-transform, and when we set z equal to e to the j omega, we're able to get the frequency response. And I'll be emphasizing in beginning of Chapter 3 that e to the j omega sweeps around the unit circle in the z-plane. So it's like we're putting a cookie cutter. If you are into baking and cutting out cookies, you can visualize it as cutting out a strip, a circular strip around in the z-plane, and that is, if you peel that out and lay it flat, that's our frequency response axes. It's complex, so it has real and imaginary parts. It has magnitude and phase. We can use superposition because we have linear time invariance working for us. And as I pointed out, I think last week, simple time delay system, ND sample delay, becomes in the frequency domain, it becomes this phase shift factor. So it says if a signal goes through an ND sample delay in the frequency domain or a frequency response, it's picking up a negative phase. So it has a magnitude of 1 and it has a phase of minus omega ND. So as frequency goes up, as ND increases for a given frequency, the phase shift increases. So we have an angle that changes with time delay, and that's an old concept from continuous time signals and systems, for sure. And of course, if we want to, we can develop a theorem, and we'll have that delay theorem here coming up a little bit later, that just says if we want to look at the frequency response of an unshifted delta function, that's just going to give us 1 if ND is equal to 0, and then we can say what is the ramification of having a delay that is creating this linear phase. And I guess I forgot I have it expanded out here. So unity gain or unity magnitude response, and then a negative phase slope minus omega times ND. I mentioned this last time, and we went through it. I'm going to just detail it a little bit more. If we want to look at, instead of the complex sinusoid, we want to consider a real sinusoid, such as cosine omega naught n plus phi, we can break that from Euler's identity into a positive and negative frequency complex sinusoid, and then we can use the linearity fact that we have linear time invariant systems, so we can superimpose Fourier transform, or this is the Fourier transform in the end of the impulse response, so we can use this idea over here, linear combination of complex exponentials, and that's how we can then get the special result for the cosine. What I didn't go into last time is how do I know that I can carry this all the way down to here? And the trick is that if I want to develop a little theorem, and this comes up under the symmetry properties for the Fourier transform, if I want to replace omega naught by minus omega naught, because that's what we have in here, how do I know what the Fourier transform or frequency response of that is? Well, I can just plug into it directly. I'm going to plug into the minus j omega naught, so that has changed the sign in here. And then the trick is I pull a conjugate out of that. When I pull a conjugate out of that, I end up having to counterbalance that with an extra minus sign. And if this is real, the conjugate doesn't have any impact on it. So this is kind of a sneaky little mathematical trick to just say, hey, if I have a real system, e to the minus j omega naught is equal to h conjugate of e to the j omega naught. So what that allows me to do then in the factoring over here, if I can now replace this by h conjugate e to the j omega naught, and then I can pull that out front and as a magnitude, and then on the inside I've got a plus and a minus in here, or minus and plus, I guess. I said it wrong, but at any rate that forms back into the cosine, or that contributes back to the argument of the cosine, the angle response. So this is an expected result, I would say, and it's a very nice result. It just tells you that in the case of the real cosine going through a discrete time system, it picks up a magnitude change and it picks up an argument of its phase response inside the cosine. And after all, that's like the one I mentioned last week. To me, it's when you first sit down in front of an oscilloscope and you put a cosine wave into something on your breadboard and you look at it, the input and the output, and you say, hey, that's a concept that you now carry the rest of the way through. We get the same cosine wave back, we see a different amplitude, and we see it phase shifted. I think actually I can show that really fast because I think it's already in my notebook over here. Let's see. I was reviewing this before class and I thought I saw it in here. That's amazing. I can't see it right now. It was right here. Oh, there it is. Jumping way ahead, just pass a real sinusoid through a system. So here, I just create a cosine sequence, give it a digital frequency of 0.02, and if you take 2 pi times that 0.02, that's now my omega naught, as I point out over here. And then I run it through the filtering function with the coefficients for a filter that has impulse response a to the n u of n, and we'll keep coming back to that. Its coefficient, in this case, to make it unity gain, is to put 1 minus a for the numerator coefficient in the representation, and then 1 comma minus a. And we're going to work through that Fourier transform separately or shortly, but I just wanted to point out that here the blue is the input and the output is the orange. And I guess I don't have my notes labels down here, maybe making total sense, but it's 0.9 for A, and I just spread my notes around those two different markers. But the point I'm wanting to make from the example I just finished in the notes was here's the input cosine, the output cosine is phase shifted and amplitude attenuated, and it's in steady state. The transient was right out over here, and the transient is now passed us by. I mean, we've settled, and this is just staying as a sinusoid with a new phase shift and a new amplitude. Is that good? Good to go? I mean, it's, like I said, a fundamental concept. So here's where I make a comment about h of v to the j omega, always periodic with period 2 pi. And what brings that home is when you see how you can take the exponent and replace omega by 2 pi, and then I can go and break that apart again, and I can break out this piece. And that just equals 1, because I'm just multiplying 2 pi times n, so I'm always sitting there right at 1 angle 0 on the complex plane. So it just repeats again for any number of cycles. And we'll take a look at that in Python too. So generally, if we're talking about, I think I may say this later. Well, I've got a picture coming up here. Let's just consider sort of a hypothetical example. Suppose we want to consider an ideal low-pass filter with a cutoff frequency capital omega c. And the book likes to use capital omega when we're talking about the analog domain and the little omega for the digital domain. That's just the standard notation of this book. So suppose we're talking about a low-pass filter, cutoff frequency omega c. If we want to look at the equivalent of that in the discrete time domain, we would just have a lowercase omega c. And if we take into account the fact that all spectra or frequency responses are periodic, if we talk about, the omega c lining between 0 and pi on little omega for our digital filter, we're good because we don't have an overlapping frequency response. We just have this periodicity, though, showing up, and that's all I'm after here. When we get into sampling theory in Chapter 4, we'll see how we could screw up in trying to convert an analog low-pass filter to a digital low-pass filter if its cutoff frequency turns out to be higher than pi, which is like the folding frequency, and we'll get back into talking about that. I'm saying get back into it because those of you, or all of you, have seen sampling theory, like starting in 2610 here at UCCS, and Lantu, you took your undergraduate degree somewhere else, right? But you've seen sampling theory already.
I took 2610.
Oh, you did? You took it here? Was that a requirement? Okay. Well, that's cool. You had somebody tell you that because that was part of your admission, maybe. Okay. That's good. Years ago, we didn't have a class like that, many, many, many years ago, and I was a huge advocate for having that class because computer engineers in our program have that class, and even though they don't stay with signals and systems all the way through, they at least see that first semester class, and I think that's helpful for computer engineers. Something that computer scientists never see. And when you start working in industry, you will be bumping up against those two types of degrees fairly frequently, or at least that's my experience working as a consulting engineer. I'll see a person that likes the computer a lot, and I'll ask the question, are you a computer engineer or are you a computer scientist? Oh, I'm computer science. Okay, so when I start talking signals and systems, things start to kind of zoom over their heads a lot faster than they would for a computer engineer. So that those differences are in there, and your team, it's just reflected in your team, is what I would say. I'm not working for a company now, though, that there really are that many computer scientists. I think they're mostly computer engineers and electrical engineers because they're working on embedded systems, still doing almost all programming, but they still know signals and systems a little bit, which is good. Now let's take on another example, which is to go back to the moving average filter. And the moving average filter, in the most general case, could take samples from the future and could take samples from the past. At this point, we can model things as a linear time invariant system. Whether or not it's causal doesn't destroy whether it's LTI. And I think that was hopefully brought home in the homework problems. Admittedly, as I've graded different people's papers, there's been some little bit of confusion in there, and I hope to get your papers back in the next few days. I just have to sit down and keep going on it to get it done. But let's just tackle this problem and look at what we would do with our definition of the Fourier transform or the frequency response. So just plug it into the definition. We have the impulse response is 0 except on the interval minus m1 to m2. So we're going to have this sum from minus m1 to m2, and then we have the gain constant, which makes the averaging have unity gain in our moving average filter. And right away we have to do, we'd like to complete the sum, so we have a closed form solution, and lo and behold, what reappears once again? Geometric series. Is that exciting? To me, it's exciting because you get to just keep plugging into it and moving on. You don't have to sweat details out about it. So It is a geometric series, and in this case, what helps you see it better, or at least helps me see it better, my pen died right there, but pulling the n outside, and we have a minus j omega that I missed too. So we see the ratio that we saw earlier, frequently denoted as A, is now e to the minus j omega. And we can get this series to sum, and we use that summed form right here. It's a finite geometric series, so we're good for any value of omega. We don't have a consideration there, so we're good with that. We could pause for a moment, but I don't know. Do you have any problems with this? Something just hits me when I look at it. I'd say the denominator has 1 minus e to the minus j omega. And what happens if omega happens to be equal to 0? I get 1 minus 1, and now I have 0 in the denominator. What do you think is going to happen, though, from past experience with this type of situation? Something that you learned in calculus a long time ago. Remember L'Hopital's rule for calculus? You just think about that. If you have an indeterminate form down here, and then you think about what is the limit as omega goes to 0 in the top, and if you have a situation like that, you just take the derivative of the numerator divided by the derivative of the denominator, and then take the limit now as omega goes to 0, and it will work out. And we'll see when we get into the z domain that we actually have a pole and 0 cancellation going on in here. It's not immediately obvious right here, but I'll point that out in chapter 3 when we see that again. So we get this form. It's kind of nasty looking because we have those two complex exponentials in there. What can be done, and I don't really have the details in here because I've skipped over them so that you could have something to tinker around with if you wanted to. And this is done frequently in solutions in the book and in homework problems where you can factor something out from the numerator and factor something out from the denominator, and then you can manage to form a cosine in the top and a cosine, or a sine in the top and a sine in the bottom. So this is just using Euler's identity for sine, right? So we get to do that, and that's how this equation comes into being, because if we form two of these, one for the numerator and one for the denominator, then that cancels out and goes away. So we can just visualize how we would factor in the numerator to form one sine, and it has half the argument of what we start with, and then we do the same thing in the denominator, and it has half the argument of what we start with, and then what sits out in front is the other half of those two arguments are sitting right over here. I don't expect you to say I see every last bit of it, but does the concept seem about right? It should be kind of close. And this has got a special name. MATLAB had a name for it, and I'm trying to remember what name it used. For some reason or other, I haven't used MATLAB so long, I can't remember what it called it, but it's the sine nx over sine x is what I call it typically. So sine nx over sine x, and it's sort of the discrete time version of the sinc function. So the sinc function looks like this, sine x over x, whereas sine nx over sine x is what we have in the discrete time domain. And later on, when we get up into sampling theory, I'll talk about the fact that, and this can make sense to you right now, the spectrum and frequency responses are always periodic. So in the case of this moving average filter, we get a sine nx over sine x function, which gives us the periodic humps that we see here. We're seeing a main lobe centered on 0, then the next one at 2 pi, 4 pi, and so on, and then in the negative direction. If we were working in the discrete continuous time domain, we would just have a single sine x over x sitting right in here. So what I'll say later in chapter 4 is that if we were to take and overlap a sinc function, the sinc would sit here and it would have tails going over here, place another sinc function here and it would have tails going over here. All those sinc functions up and down the axes were allowed to trickle together, we would get the sine nx over sine x. Is that believable? So that's why I will call it then this alias sinc function becomes the sine nx over sine x. Right now, is that satisfying? It is like a low-pass filter. It's an averaging effect, and it's just the discrete time version of what we'd have for a moving average filter if you created it in analog electronics. This example, complex exponential now, is an interesting thing in the book that I integrated into my notes many years ago. I don't get very excited about it anymore, so I'm skipping it. Heart of the matter, though, is Fourier transform of sequences. What we've already seen for the impulse response is in reality just generalized now to saying any sequence, we can consider its Fourier transform. The impulse response becomes the frequency response. A sequence becomes the sequence's spectrum. So this is the forward transform. The textbook in the literature uses the term DTFT, or this would be IDTFT. Later on, we're going to have DFT, but that's the discrete Fourier transform. That's closely related to the fast Fourier transform. It is not the same as the DTFT. So that extra t in there, discrete time, is a continuous function of little omega. And that's what we have going on in here. When we look at, well, actually I got these arrows backwards. Let's keep that up. I'll just start over again. Okay. So, and the DFT is just to be defined later. So don't get them confused. Just think the DT just means it's a continuous function of omega. It has all the frequency precision that we care about. And the pain that goes with to get that reward, we have to put up with some pain. And the pain is to go back to the sequence domain, we have to do an integration. Whereas when we talk about later with the DFT and IDFT, that's just a fast Fourier transform. We can do that numerically without a problem. When we go to compute the inverse Fourier transform, we can use any 2 pi interval that we choose. We're not restricted. So you go back up here and look at this definition, the first line. We can move that around. We just have to integrate over 2 pi. Any 2 pi interval works. And if we have symmetry, then we can take advantage of symmetry too. The forward direction, though, is the entire axis. So maybe ponder that for a second. The sequence is, in general, aperiodic, so it just does something. You have to consider the entire time axis if you want to get the Fourier transform of a sequence, whereas getting back to the inverse transform gets back to that sequence by just integrating over one 2 pi period. So it's not very symmetrical in terms of how it functions. Can also be considered as a complex exponential Fourier series that has coefficients x of n, and that's kind of something we'll get into studying when we study the DFT much later. So when you talk about a signal as opposed to an impulse response, we have, like I've already said, a magnitude or amplitude spectrum, and then we have the phase spectrum. And when we plot, we frequently use the principal value, and the principal value just runs between minus and plus pi. And that's what MATLAB used when you were using it years ago, and that's what Python uses too, no difference. If we need to do unwrap the phase, we have an unwrap function. We'll talk about that in chapter 5 when we get up to that point. So I have a little proof in here just to show that yes, you can synthesize the sequence from its Fourier transform. If we put in the forward transform on the inside, and then integrate it over 2 pi, normalized by 2 pi, we get back the sequence, and the initial thought is this is going to be hatted, as if to say it's an estimate or approximation. We don't know it's exactly the same, but we're going to show that it is indeed the same right here, to say that x hat of n does become x of n. And what we do is interchange order of integration and summation, something that mathematicians take care in doing. I'm going to explain how we can do that in a second, but I'm just going to go ahead and boldly move the integration to the inside and then do the summation secondly. So move the integration to the inside, and we get this special integral that becomes the sinc function. This is the type of integral you would have seen in probably 3205, I guess, with Dr. Tromboli. He does Fourier transforms, right? Continuous time domain. You would have seen an integral like this, and you can integrate it using ordinary integral calculus. 2 exponentials come out of there, and you get to form that into a sign, and then you have a denominator term, which comes out of there too. So we get the sinc function. And the sinc function for the discrete time version gives us this. It gives us a delta function. In the continuous time domain or continuous frequency domain, we wouldn't have the arguments like n and m. Here we do have n and m as integers. So if it's just an integer, then the sign of pi times an integer is always 0, right? And then if that integer happens to be n minus m happens to be equal to 0, then the denominator goes to 0, and then we use L'Hopital's rule, and then we find out that, lo and behold, it's 1. So it behaves like a delta function in terms of integers n and m. And if we put that delta function inside this term up above here now, so it goes up there, and it's plugged up right in here, and that delta function then sifts out x of n. So we get the desired result. We've gotten the proof that inverse Fourier transforming gets you back to the sequence perfectly, provided you can interchange order of integration and summation. And this is an advanced calculus kind of problem, which my PhD advisor had me take advanced calculus. I took a couple semesters of it, so I got an appreciation for it. So when I first started teaching, I decided I would use it a little bit in some of my notes. So this is an advanced calculus idea, and it just says that x of m, the approximation, is x of e to the j omega to within an epsilon, and that epsilon can be made arbitrarily small if we want to. So we can get n as a function of epsilon to be as small as we desire, which means that the difference between those two functions is shrinking to 0. Now, what conditions in our functions allow that? The sufficient condition for that is that x of n be absolutely summable. And this is pretty important to us because we put a lot of weight on this as we go forward. Absolute summability as a sufficient condition just says that the sum of the absolute values of the sequence are less than infinity. Where did we see this just last week? Is that a really important theorem? LTI systems are stable if the sum of the absolute values is less than infinity. So we now have it hold for a system, and it also holds for a sequence. So we have the same idea. So system an impulse response and a general sequence. It could be an input or output or something. Their Fourier transforms exist. A sufficient condition is they be absolutely summable. So stable LTI systems are really important to us, so they're going to be absolutely summable, guaranteed, right? From what this shows, we know that it has to be bounded, so it also satisfies the sufficient condition to have its Fourier transform exist. Sound good? However, not all sequences that we care about are absolutely summable. So then we have a lowered class of signals or sequences that are mean square convergent. And mean square convergent means you have to give up the uniform convergence. That's nice for having a nice continuous function of omega, but we still get some useful properties. So this is called square summability, and it just says the absolute sum of the squares. And one of the homework problems I was grading, I wrote a note on somebody's paper. I'm not sure whose paper right now that I wrote it on, but remember in math, in calculus, the harmonic series, that's the sum of 1 over n from 0 to infinity. What do you remember about that sequence? The harmonic series. It's called the harmonic series, but it diverges. So, however, if you were to take a 1 over n sequence and make it be 1 over n squared, then it does converge, and that's exactly what I'm saying right here. Magnitude squared is a more powerful summability require. I mean, it puts more power on it, but mean square convergence, which is what this is, means that if you're approximating a signal with m terms and intending to make m go to infinity, and it's only a square summability type convergence, then it's not perfect. And it says that for some values of omega, the error may not approach 0. And it's fine for me to say that, but I'm going to be showing you that in the next example. So you're going to see firsthand how this can come up and bite you, and how we just have to learn to live with it and understand it. And your background, though, you studied square waves a long time ago, and square waves aren't absolutely summable either. Remember the ringing that happens if you try to approximate it? But in the analog domain, I tend not to worry about it as much because the rise time is not 0 in any analog waveform, although you can still have a Gibbs phenomena happening. In the discrete time domain, it's for real, and you can't really just brush it off. You have to cope with it. So let's take an example of that. Consider an ideal low-pass filter. Ideal low-pass filter, which we just looked at a few moments ago, would have this sort of a form that you see right here. We have a cutoff frequency. Now that we have played a little bit with forward and inverse Fourier transform ideas, let's just plug that ideal filter into the inverse Fourier transform right here. This integral is very much like an integral that you see when you're studying the Fourier transform for continuous time signals. It becomes a sinc function. It's a scaled sinc function, but it's a sine omega c n over pi n, and this is got this nasty n in the denominator, so it harkens back to the harmonic series as not being absolutely summable because of that 1 over n. But it is square summable, so it has summability in the square summability sense. So we can go ahead now and just see what is that price that we're paying, go back to seeing how well this impulse response, because maybe this is something that you've been just hoping you could do with digital signal processing. You could build an ideal low-pass filter, and this right here says, oh, all I have to do is implement this impulse response, and I can build an ideal low-pass filter. But there's a couple of problems with it. One problem should be obvious from the homework that you've turned in already. What's wrong with its impulse response from a causality standpoint? It's non-causal. In the way you can make it causal, you can take it and shift it over to the right, but then you have to be willing to truncate it, which means you're going to maybe use only m terms. So if you took, or 2 m terms, I guess, in this example here, and slid it over to the right, you'd make it causal, but now you don't have but 2 m terms in there. So if you look at what this function looks like, and just plot it out as m gets bigger and bigger and trying to approximate this ideal low-pass filter, you see that you're getting something that looks like more like a low-pass filter, but the fact of the matter is the ripple here and the ripple over here are the same. So no matter how big you make m, this filter still has ripple. It has ripple in the pass band, it has ripple in the stop band. Extremely irritating. Agreed? Or if you were there, you'd say, why can't I get rid of that? And the ripple is so large that it's only, I forget how many dB down it is. It's around, is it 17 or 19? I don't know. My brain is wigging out on that. I've got an example of this in the Jupyter notebook for this part of the notes. So we'll come back and look at that a little bit later, probably in the Jupyter notebook, and then I've got another example further down in this chapter that we'll be getting to later too that is also irritating because of this same phenomena. It has to do with spectral analysis there. It's another sort of manifestation. It's a similar type of thing now. If you're trying to build a low-cost spectrum analyzer. What? Yeah.
If instead of having sine omega c n over pi n, what if you had it over pi n squared?
You could do that. You're talking about right in here, right? Mm-hmm. Then the shape of the filter would be...
Would it not?
It would not be flat. It would not be flat. Let's try. We can try that though, because I think I've got it. I think I've got that in the Jupyter notebook. I'm not positive if it's there or not. Maybe I can find it. There's the alias sync function. Yeah, here it is right in here. So there's a low-pass filter that has 21 taps in it. It goes from -10 to +11, and it's truncated like that. So and I guess it looks like I added this in later. Yeah, this one's got 61 taps in it. So let's take those two and just compute the frequency response. I've gotten ahead of myself because I haven't talked about the freq z function in here, but it is a function that you can use to calculate the frequency response given the impulse response. So that just shows you those two filters together. The first side lobe is down -21 dB. I wasn't remembering that quite right. But now, what you said was
if you square the n and the denominator.
Yeah. So it would be here taking the sync function and then dividing through by another n61, which is going to have a problem when n is equal to 0. So I don't think that's going to work without tweaking it somehow or another. Yeah.
Okay. But if you didn't have n equals 0, like if you shifted it,
Yeah.
would that?
I could work on that. You're challenging me to do something tonight when I don't want to grade papers, like just my brain is usually pretty fried when I get home, so I could build this up into example. I could do exactly what you said. I could shift it over and show you.
Would it be absolutely summable?
No. Well, yeah, I guess it would be absolutely summable, but it's not going to be a flat response in the passband is the thing that's the big demonstration point that I would throw up in there. But there is a solution for this, though, and that actually is in this notebook. It's called windowing, FIR filters. So there's a particular type of filter called FIR win, which is exactly what we're talking about, the sin x, the sync function kind of response, but then it applies a window shape on top of that. So rather than having it just be that sync that tapers and gets truncated, it provides some sort of an overarching shape, not as powerful as the 1/n, although that's a type of window in a sense, but the Hanning window, for example, is what's used in this example. I'll just jump and look at it since I've already got it here. So those are the two impulse responses, and then I compute the frequency response, and you can see that the rectangle, which is just doing nothing, only has the first side lobe down at -21 dB, but then with this hand window or Hanning window, it's much nicer. And the idea is you can take that more into an extreme and get more into that. You can see that I got carried away with this. It's because I already got you excited about it, right? You're interested and you're like, what can we do to beat this? There's things to be done, plenty of things to be done. People got intrigued by this a long time ago, and they figured out ways to deal with it, and that's what the windowed FIR idea is all about. And then there's a bunch of other low-pass filter design techniques. Okay, so we talked about absolute summability is the most ideal case for getting the Fourier transform of a sequence or impulse response. Square summability is what we were just bumping into with the ideal low-pass filter. And then there's another case, special case, that's neither absolute or square summability. And these types of signals require impulses in the frequency domain, and they're not strictly physically realizable. They're just nice to have included in the family of waveforms. Just like in the continuous time domain, you got introduced to using a delta function to represent the spectrum of a sinusoid that runs forever. So we do the same thing here. We say we just like to be able to have an impulse, the spectrum of an impulse, and it's just a nice idealization for modeling purposes. It's not something that you would ever actually encounter. Now I say encounter because if you, and that's another example that I drill into, and that gets into the spectral analysis problem. If you have lots of cycles of sine wave and you just truncate it, and take that into your processing engine, it looks very much like a delta function. It doesn't have any other issues, but if you don't have a lot of cycles of that wave, then you get something called spectral leakage, and that I'll drill into too. This is all interesting stuff, and up until relatively recent past, we didn't have, back in my generation of growing up, an oscilloscope was an analog measuring instrument. Nowadays, an oscilloscope is usually a digital oscilloscope, and if it has a spectrum analysis capability built into it, like it can take an FFT, then it has window functions and things like that associated with it to make that spectrum look more like the continuous time sinusoid spectrum, where it's a single spike, a delta function spike. So in the discrete time domain, we carry that forward, and we have an impulse train. Why do we have to have an impulse train? It's because if it's going to be a valid spectrum, it has to be periodic. So just remember that too. Remember I mentioned that a while back tonight. Any spectrum in the discrete time domain is always periodic with period 2 pi. So this makes the spectrum of, say, a complex sinusoid, which is what this is, look very complicated, because to have an e to the j omega naught n, to have a Fourier transform being a delta function, it actually has to have an infinite number of deltas. And how do we get around that or make that seem more not so nonsensical? You would just consider what lies on the interval minus pi to plus pi. It'd be that one green delta function, and then there'd be another one to the left and another one to the right, and covering the entire axis. So what happens is we just focus on the interval minus pi to plus pi, and then we're good. But the delta function doesn't replicate itself, whereas something that's a function of e to the j omega automatically is a mod 2 pi function. Remember, I pointed that out quite a while back tonight. The delta function doesn't have that property, so in order to make it become periodic spectrum, the sum has to be put on there, and it makes it look very messy, and we'll bump into that another example tonight.
Dr. Whitaker.
Yeah.
I'm a little bit confused. Is the summability, do we care about that because you can't take the DTFT of a not?
Absolutely. That's right. That's right. We have to replace it with this, and this doesn't have certain properties. It loses some of its power later, and I will try to point that out to you.
So to be able to take the DTFT of this one, we would have to truncate outside of negative pi to pi?
Well, to take the DTFT of this one, we just have to say it's this. We just have to kind of wave our hand. It's called Fourier transform in the limit, to say that we can get it as a delta function. And then we have that nasty little delta function sitting in there, right? That is not mathematically manageable in the same sense. I mean, to me, it's kind of like a delta function is you try to grab onto it and it squirrels away from you because it's this special function that has zero width and its height is not infinite, and it's just a mathematical concept. It has an area equal to 1. Don't get me wrong, I like delta functions because they're essential in modeling, and seeing a little bit of electromagnetics up here makes me think of when I took advanced electromagnetics as a PhD student. We used delta functions to model charge distributions too. So, and you use it in probability theory to make approximations for certain types of distributions. So delta functions end up being used in a lot of engineering things. They're just convenient, but you have to be careful how you handle them. So here we could have a bunch of different sinusoidal spikes superimposed. Well, no, this is for a constant sequence. So a constant sequence would have a spike at DC, and then it would have more spikes at multiples of 2 pi. And if we have cosine omega naught n, very much like the continuous time version, we get the positive frequency and negative frequency, and then the next image up are those guys at plus and minus 2 pi, and then so on and so forth. So this should be kind of familiar from continuous time, except that it's periodic now. But the idea that if you had a cosine omega naught t, that would be, its Fourier transform would have a delta function at capital omega naught, or that divided by 2 pi would be f naught, and then it would have 1 at minus f naught as well. These are just convenience things, and make use of them. And then if you have a superposition, this is what I was thinking of a moment ago, many different frequencies, you could have lots of different sinusoids all being periodic. So this outer sum is only to make sure that you've got the periodicity in there. It's the inner sum that's really the interesting thing, saying that you've got a bunch of different sinusoidal spikes, and this would be like in a complex sinusoid case, and you're trying to identify those and keep track of them somehow or another in some signal processing, like those might be signals of interest being modeled as delta functions, not having any width to them, just in a simpler model, not with modulation present. Okay, looking at the clock, we're doing good on time. So the big function for working with Fourier transforms approximately in Python is, it's in the scipy.signal package, which makes me think of another person's paper that I graded that didn't realize that L-filter existed. Remember we talked about L-filter last week, and you use it in your homework, but that comes from scipy.signal, remember? We always were, let's just quickly look at what goes on over here in Python. Essentially all the time we're going to be importing scipy.signal and I just give it the shorthand name of signal, and that brings us L filter, freq Z, Z plane, a whole bunch of other things that, well, Z plane is something that I wrote, never mind, but it gives us a lot of functionality. And then SIGSYS is built on top of signal, scipy.signal, and its definition, and that just augments it with other things. So unlike MATLAB, where everything was always available because of the way MATLAB worked, Python is more like C and C++, where you have to import packages to get stuff done. You have to import NumPy, you have to import matplotlib, pyplot to get your graphics. From what I could see from grading papers so far, as everybody seems to have gotten somewhat on board with that. It should just become sort of like, I gotta have it. I can't use Python for signal processing without these pieces. You might do something else with Python that doesn't require NumPy or graphics or signal processing, and you might only have NumPy, let's say, but we'll always be using those packages, so they just have to be there. So here's an example, getting back to a sequence that was it's a rectangular pulse function, and it goes from 0 to 6, so it includes 7 total spikes. And if we plug that into the Fourier transform definition, we're just summing from 0 to n. That is, again, a finite geometric series, and we can get that response very easily by simplifying it. This is, again, very similar to the moving average analysis, except now it's a spectrum rather than a frequency response. And then we also have the convolution theorem, which will be talked about probably right after the break, which says if we're passing a signal through a system in the time domain, that convolution becomes multiplication in the frequency domain. So this is the spectrum at the output in that particular case. So all of those things are kind of drilled into in examples that follow, but they all rely on the use of signal.freq-z, and there's a lot of different ways of using this function. This form right here will kind of become apparent once we look at general difference equations. But I'm not going to get into that at this moment. It just reminded me I was going to go back and spend some more time with difference equations, but I slipped over that. Maybe I want to think about that during the break. There's a particular way, though, that I like to use freq-z, and I'd kind of like to have you get in my camp if possible. So how do I get you in my camp? I have to show you an example of how I like to use it. If you remember, there's a freq-z function in MATLAB, and it works in a somewhat different way, but it had a bunch of options. The signal.freq-z has got a bunch of options too, but the way I like to use it is kind of like what I'm going to show you here. Suppose I have just like a moving average filter or a rectangular pulse. I'm going to take the Fourier transform of that, the DTFT of that. I drive the function with values, omega values, but I start by driving it in terms of what I call the normalized digital frequency. Admittedly, the transform is always a function of omega, but I myself get annoyed by having to do plots that go from an inexact number of, say, minus pi to plus pi, or from 0 to 2 pi. I'd rather get rid of the 2 pi factor, so I divide through that and call that and the book calls it normalized digital frequency, F. So F is in samples per hertz, whereas omega is radians per sample, is what we'll see in chapter 4. So when you do that division, I have a number that goes from either minus 1/2 to plus 1/2, or from 0 to 1/2, which to me is a nicer plotting axis than 0 to pi. Does that make sense? So here what I do is the function frequency will return 2 arguments always, and you have to make sure you pull them both out. The first one is W, or omega, is what it stands for in the frequency notation. The second one is the complex value, the Fourier transform X. So I can't get rid of this. I just have to let it sit there, but I don't do anything with it. And instead, I'm driving it with omega. So I'm giving it a specific range of values I want for omega. It could be a single point. It could be 2 points. It could be multiple periods of 2 pi. You can do it any way you want to. But in this case, I'm just running, in the way I defined F, it's just going to span from 0 to 0.5. And you can see that in here. It's actually going to be 1 point less than 0.5 for 1024. It's just a small amount, though. So I do that picture, and there's what the magnitude response looks like. It looks like the moving average filter's frequency response magnitude. And then I can take the phase of that. And what I'm really doing is I'm using freq z in a way that's a little bit twisted. I'm pretending that the denominator term that shows up in the definition over here just making it set equal to 1. So what's in the numerator is really just like the Fourier transform of a sequence being approximated with a finite number of terms. If it's a rectangle pulse, it's exact. It only has so many terms. If it's many other sequences we're interested in, it only has so many terms. And then you can just make this be as long as you need it to be, and it will manage it. It depends. You have to be careful, though, in that you have to make the resolution or the points in the frequency axis small enough. So here I chose 1 over 1024. Maybe that has to be 1 over 2046 or 4096 or something like that, just to get enough resolution. And you need to play with that when you're doing plots for homework problems. In other words, if you have it draw a picture of a frequency response and it looks kind of jaggy and kind of not very smooth, remember that the Fourier transform of a sequence, if it's absolutely summable, is a nice smooth function in omega. It might have a lot of fluctuations in a narrow band, in which case then you'll need to increase the resolution, but it should not be something that looks really hacked up. So I will write on homework papers a lot, use more points. Don't be so cheap. I mean, your computers are fast. Just draw a nice smooth function, because that's what it is. It's a function of a continuous variable omega. So don't be cheap with it. You know what I'm saying? Don't be crazy, though. Don't put 2 to the 20th in there or something like that unless you need it. But just get a nice smooth looking picture. So there's magnitude, there's the phase, real and imaginary parts. Those are properties we haven't actually gotten to yet that are over here in the notes. But what example did I have in that? Yeah, I had this. Actually, the very first example, this is one we'll look at. I guess we'll take the break about now because we haven't gotten to the theorems yet. This gets into some of the theorems and transform pairs, but this is just this fundamental difference equation. Y of n is a times y of n minus 1 plus x of n. This from the classical solution of difference equations, which we did last week, and I wanted to hit that up a little bit more, has impulse response a to the nu of n. So these two go with each other over and over again, a to the nu of n and this first order difference equation. Some of you have probably noticed that, or if you haven't, I want you to just sort of say, these always show up together, they're synonymous. And guess what they're synonymous with in the analog continuous time domain? The RC low-pass filter. They're that same exact shape. It's the discrete time version of a low-pass filter, but if A happens to be negative, in this case, it can be a high-pass filter. So it's kind of cool the way that works out. A few other little details, but I'll take the break now, and I'll probably start with the Pi audio demonstration, just so I can show you how that works, and we'll listen to it and just see how that real-time DSP stuff works, since it's an important part of the class. Resume recording. So we're back. We're going to go through a little demo of Pi audio, and this will become important. You may want to play with this earlier if you're taking the lab. Did you do lab 2, or you use Pi audio already?
Yeah.
Okay, so you've seen this before. Just to go back over here, what I'm going to show you right now, I pushed it. It's embedded in the project, but if you wanted to play with it in a simpler way, what I'm going to show you is right here. I just zipped up from this computer before I came to class. I played with it earlier on my MacBook, and this is a different rendering of the same basic idea, but when I had you install Python, you installed Pi Audio, and that's important that you have that. You installed the widgets. Those are two things you need to have to do this. And then the current version of Pi Audio Helper is on GitHub is not working properly. It needs to be fixed. So right now in this package, this zip package, I'm giving you the old version, which works well and actually needs to replace the new version, which my helper, Tarant, thought he was making better, and it turns out this old version is the one to go with. So I'm running that, and I've got that on here. Let's just go cold turkey. I'm going to start my notebook over again. And by the way, if you don't know what this is useful for, if things are going poorly, or if we have something go bad in the notebook where something's not calculated and you feel like something died, this restarts the kernel. And if you haven't explored this other menu right in here, you get to see your kernels that are running, and I've got 2 of them, and you can stop kernels in here too. And that's sometimes a good thing to do when you're closing a notebook. If you have a bunch of notebooks open, you're going to start having a lot of kernels of Python running, and you're going to be burdening your system down with some extra resource demand. So you can manage that in here. This is an engineering tool, so it's got all these tinkerers, what I call tinkerer's delight, because that's what engineers are. We like to tinker with stuff. So we have all these controls available. So let's launch this. So notice I imported IPy widgets, I imported Signal, I imported in place of the original Pi Audio Helper, which I didn't download. I haven't downloaded because it's not right. I'm just importing it locally, so it's right in my folder. And you can always see what's in your folder. This particular example, actually I don't know. It's in its own folder. So this is all I've got for running this notebook. It's just in this folder. This WAV file is downloaded separately, and it's on the website under the project. It's large enough that I can't put it in one zip package, because when I was forced to move to this new website that the university's IT set up for me, I can only have 8 megs in a file. So this audio file that I'll be playing and demoing is one that I created in GarageBand on Apple, and it's bigger than that, so I had to do it separately. So at any rate, I talk a little bit about what's going on here, and we'll get exposed to this when you do your project. This is being able to do real-time DSP right on your PC using the audio subsystem on your computer and using Pi Audio, which was developed at MIT, and then my Pi Audio helper, which sits on top of it. And you use the Jupyter widgets to make some GUI controls up. So internally, what is this consist of? This is a real-time audio system, and you can see on the far left there, I've got two ADCs, analog to digital converters, that are part of the audio system on your PC, MacBook, Linux, whatever, they all have it. And those frames get packed together inside. The way the audio processing works with Pi Audio, it's viewed as a packed frame that's got left and right channels in it. Then on the back end, on the far right-hand side, you see the opposite happening. The channels are unpacked into frames that go out through the digital to analog converter, and then those would be heard on your earbuds or your speakers when you do this in the lab eventually for the project in the class. You might not want your family to hear this because it might be annoying to them. My wife doesn't like this stuff at all, and you're going to be making some strange sounds too. It's pretty cool, actually. I like it. One part of the lab, though, you're going to be making some chirp sounds and things, which I know are not super pleasant. So depends on what your family is like. You might want to just put your earbuds in, though. So in the middle of this is what I've created with the Pi Audio helper. I've created a frames-based DSP engine that uses Pi Audio, and Pi Audio uses frames, and a frame is sometimes called, another name for a frame is I'm trying to remember, the names get confused if you're looking at waves, but frames or buffers, I don't know, I like frames better. So you have a frame of samples, like 1023 samples. You bring all of those in and process them at once, and then you send them back out again, and then meanwhile you're buffering up another frame. That's all handled in the background by the PC's audio system. The longer you make the frame, if I was teaching real-time DSP, I'd be talking about this a lot, but the longer you make the frame, the easier it is for the PC to manage to fit in time to do its job of processing that frame, because our operating systems are responding to mouse events quickly. They're multitasking all kinds of other things. So a long frame makes it easier to keep the frame contiguous and not have glitches and things. But a long frame leads to very long latency latency c. And what that means is if you're speaking into a microphone and listening to the back end of this thing, you will be annoyed by the latency of about a quarter to a half a second. It's very bad. It's just the nature of the PC audio system. If you listen to music, you never notice that latency because you only hear something. If you were to put live stuff in, you would notice there's a lot of latency. So this system is very powerful, but it does have a large amount of latency. So in order to make it more full-featured, we make use of globals in the notebooks, and we make use of the iPi widgets to provide controls to control attributes of the running algorithm. And all this runs in Jupyter Notebooks. So the first thing we do after we load up Pi Audio Helper is we want to see what devices we have on our system. So I just ran that line, and you can see on my Windows 11 tablet here, I've got all these devices available. This is my design of making it functional but kind of crude. Every device is managed by Pi Audio Helper as an index. And the indices are numerical values. They start at 0, and depending upon your machine, on my MacBook, it doesn't have all kinds of other things, but here, on my Windows machine, it just enumerates all kinds of devices, and you guys will, if you have Windows laptops, you'll probably see this too. And because I'm connected through an HDMI connector to this to the system here in the class, what do we see? We see some things that Crestron, that's the interface that I'm connected to. So it's even mapping all those devices so I can do things there. And then Beats Flex is what I'm talking on right now. It's got those guys defined too. And I may have to do something to hear this. I'm not sure because my Beats Flex is showing up out here a lot. What I want to do, this is different than what I had at home before I came over here, but I restarted Pi Audio Helper. So if you're moving your computer around and you're on and off devices, when you go to play with this, you might want to do a restart on the notebook when everything's plugged in the way you're going to use it to make sure all the devices show up properly. Because if devices are gone and you put a number in for that device and it's no longer there, it's not going to work. So you want to make sure it's enumerating properly. So right now, my idea was I would pick as my input my microphone on the Realtek audio of my PC as 1, and then I could come out on Beats Flex headset, and I could hear it if I plug these guys in my ears, but you won't hear it, so I'll have to probably mess with that. So I'm going to go for Realtek on 6 and see if that works. Well, it'll be kind of a trial and error. So 1 and 6. I'm just going to do one example. It's sort of a more exotic example, not what you're doing in the lab. This is going to be stereo. And because I was going to pop something in my bag, and I don't think I did, I've got a USB device that I can plug in that provides stereo analog inputs. It used to be all PCs would have that. Nowadays they don't. You have to buy something separate, like maybe a headset like this or something, so you can plug a line in from some other device. So what I do in all these demos and what you're going to do in the project, you're not going to be taking a live value in of your own. You're going to be using another Python class I wrote that allows us to take a pre-recorded WAV file and put it in as an object that will loop on itself, so you can have it loop over and over again. And it will be like something live, but it'll be something that I've created, so you don't have to worry about getting a microphone, because everybody will have something different, or you'll simply have nothing. You won't have any devices that you want to record off of. So we create some widgets, and I just created the widgets. I've created a slider for gain, and I've put some parameters in. I've created a right and left gain slider, and if I was to uncomment this, you see there's my widgets. I can move things up and down. Parameters are changing. You can see the little, notice the flickering going on up there. You can just tell that it's active. It's doing something. But those widgets are not connected to anything right now, so you can check them out, and if you're playing and creating widgets, which you'll have to do in the project eventually, you can do that, but I'm going to hide them. This is the heart of the DSP. It's called a callback function, and for those of you that have done microcontrollers, microprocessors, this you can think of as an interrupt service routine. Does that make sense? An ISR. It's like something is calling this function to do something. In this case, it's Pi Audio through the audio subsystem. The audio subsystem is saying as soon as a frame of data samples is ready, it's in data. This callback function is bringing in data, and frame count is the number of samples that are in that frame. As soon as it's ready, this function fires all by itself in our notebook. We don't have to make it do it. It's going to do it by itself, and it's going to process the samples. In this case, I'm not bringing in anything from in data because I'm not connecting up a microphone. Instead, my surrogate data is coming from this buffer object that is is taking in data, but I'm not actually going to use it. I'm going to use a circulating buffer that I have. So at any rate, that is at the top. This will get explained more when you do the project, but right now the main thing that I'm doing is a frame is coming in, and I'm getting it from this object here called XLoop Stereo, and it grabs a frame count of samples to act like it's the frame count of samples that the audio system's bringing in from the microphone. But I'm faking it. I'm grabbing samples from an object that I created outside. And I'm going to pass those samples, break them apart into stereo. Index 0 is left and index 1 is right. And I'm going to scale them up to be integers as they get processed and sent back out of this callback. And then what I'm going to do is take those values of these buffers left and right and multiply them by a gain value, which if you see lgain.value, lgain is this widget object that was created, and it has an attribute called value. It was initialized at 1, but it can take on different values. So that's going to be the action of the slider. Does that make sense? Signal is going to flow down through this code, and the slider value is going to gain the value that's coming out of this circulating buffer up and down by our controls. And then we pack it back up into left and right. We have to convert it from float values back to fixed values, and that's right down here, converted back to an assigned integer in int16. And then I have some other things that I included for monitoring the callback, but we won't be using that here. And then finally it goes back out through the end of this callback to using 2 bytes, and I pass back something that's part of Pi Audio 2 on the internal. It's just making it happy so that it can respond to the callback. But we initialize everything right here. We bring in our WAV file that we're going to make a buffer, a loop, and then we put it into a loop object down here. And then finally I create a top-level class function called DSP IO stream, and it's going to have a function that it calls in this object. It's called callback. By no accident, it tells me that's the name of the function it's going to call. And this will be real important when you do the project. You want it to call a function that you're giving it, namely the callback function that processes the audio in real time. And we get to specify the sampling rate, and these 2 numbers correspond to the input from the microphone, which we're not going to use, but we have to fake the audio system into thinking we're using it so that it can function properly. And then we're going to come back out on 6. And this last parameter here just tells we're going to loop indefinitely by not looping for a second or 20 seconds. Instead, we're looping for 0 seconds, which makes no sense, right? It's just a numerical value that means loop for forever. And then we set up an interactive stream method on the DSP IO3 that has 2 channels, and the parameter 0 is infinite stream also. And then here's where our widgets get brought in. So the widgets will fall below. And what did that happen? It's because I didn't compile my callback. I'm pressing Shift-Enter. So now they're here, and it's running. Just increased the gain of both of them. I don't know if you could tell from there. I don't have it playing in the room because I don't know how to do it. Chances are there's an interface on this console that I can bring up audio in. But then I'd have to go probably on your PC under sound settings. Yeah, I could pick something else. I don't want to mess with it. Are you able to hear it though? It'll be more meaningful when it's right in front of your head. And you've played with it. Has it worked well for you?
I didn't play with the different games, but
Okay.
the audio stuff like
Then you can stop it. So there's a lot of other instructions in here. I just wanted to show you how I went through this, and I wanted to give you something that you can go play with and see if you can get it working yourself. So you can come back and watch the video and see how I got it going. It's worked quite well, but it cannot work too, and then you maybe have to restart the notebook. You might get an error message in here, like if I go home tonight and open up my tablet to start looking at the video or something, and I try to run this cell, or if I just simply click right there, it might bomb out, and I might have to recompile it. And if things go really bad, then I go up here to the top and start the kernel and run all the cells that I need to have run to get everything going. I'm willing to bet, though, that if I wanted to have it play through this system, all I'd have to do at the top is it has 2 outputs, Crestron. I would have to put in 4. Are you tempted to try it? I'm sort of tempted to try it just because it'll take a moment, but I'll put in 4 rather than 6, which is what I've got in here right now. There it is, and there's a volume control I have here. I don't know if you can hear stereo or not, but cool. This is where you get to have fun, in my opinion. And you get to learn about DSP math, too, because you'll be filtering and you'll be doing different things. I'll demo more stuff because the sample notebook for the project has some things that actually work in it for demos, too, that you can tune filters, add noise. It's pretty amazing. I took this to a conference and had a lot of fun with it back in the day. Not quite 10 years ago, but it's been maybe about 6 years or 7 years when I was showing it off at the conference. I wrote a paper on it. The paper is, if you're interested in Pi Audio Helper, there is a paper linked and the website too for the paper that I wrote at the Scientific Python Conference. It was my dream to be able to do real-time DSP right there in the notebook. And I don't know if anybody else that quite does that yet. It's maybe nobody cares to do it though either. So you will be doing more with audio in the last project with the radio stuff. So what we want to do now is making sure that I didn't mess this up. I looked to see if I'm recording. So we had looked at the rectangular pulse in here, but what I wanted to do, just to make perfectly certain, I wanted to jump back up to the difference equation stuff that I didn't really cover in intimate detail. And the reason why I'm going to do this is because I'm starting to angle the rest of the night towards getting the homework done. So in the homework problems, I give you the option of solving, in the first 2 problems, solving a difference equation directly or solving it in the Fourier domain and then inverse transforming to get to the time domain. Okay? So you've got 2 different ways to go, and you've actually got multiple ways to go, and I'm going to point that out before we leave tonight. But we worked through a first-order difference equation last time, and this is an example of a second-order difference equation. And what happens when you have more than, when you have the second order or higher, and you just have second order, you will have the homogeneous equation that you see here, where you solve for, well, you write out the characteristic equation. There it is right there. It just pops off the page because you've got 1 minus 3z and then minus 4. And then you solve for the roots of that, and you get minus 1 and 4. And then you go about solving. In this case, we're solving for the impulse response, so we're not going to solve for the forced response and the method of undetermined coefficients. We're just going to solve for the impulse response, so we just can plug values into the difference equation, and we're trying to solve for A1 and A2. So this just takes you through that exercise of solving for A1 and A2. It's very similar to that in the homework problems, except this is an unbounded system because the roots have magnitude. Well, one root has magnitude greater than 1 and has root of 4, and the other one has magnitude 1. So it's a very unstable system. There is another example in here, though, which looks at this difference equation and just solves for the coefficients for this one. This is not really related to the homework, though, but I do talk about, in the hints page, I talk about example 211 quite a bit, and 210 are both key if you want to work with the classical solution technique. There's other stuff I want to say, but we'll get to that when I'm talking about the hints page here. What I want to do now is get us back into the theorems. So we've just come through this example of the rectangular pulse or moving average filter. There's also a big collection of symmetry properties and theorems for Fourier transforms. And they're based on certain definitions. In the past, I've assigned problems that rely heavily on this particular section of the notes. I did not assign a problem like that now. There's minimal things with symmetry. So I'm going to slip over the more complicated stuff, but I am going to home in on what I consider to be the must-know part of symmetry. So this gets involved with even and odd, symmetric and anti-symmetric, and it's basically telling you something that you probably either saw or heard about in 3205, Signals and Systems 2, that any sequence can, whether it's real or complex, can be written in terms of an even part and an odd part. And then here's how you get the even and odd parts. Then if you go through and work with the even and odd portions, you can eventually get, you'll get, of course, that the Fourier transform will be the sum of the odd part and the even part. And then you can go backwards to get the even and odd parts from the total Fourier transform. It's important in some types of work, and definitely the book, like I said, has homework problems in it. I considered doing that again, but I said, nah, I want to stay on more traditional stuff that I think is more valuable. And here, what I'm particularly interested in is extending off of what you learned already for real signals. In the discrete time domain, if you have a real signal, we always know that x of e to the j omega is conjugate symmetric. So what we find, what I mean by conjugate symmetric, I'm going to show this as two different ways of thinking the same thing. This would be By the way, the clip bar is kicking in. I'm feeling like I'm not getting stronger, but I'm not like last week. I was going downhill really fast. I don't know if you could tell, but I got home and I'm like, wow, I'm tired. I had to eat some food. I mean, if you're really lean like me, you find if you don't eat, you can't stay up. So I have to learn that at an old age over and over and over again. I've been out, you know, running with my dogs today, and what else did I do outdoors? I mean, I'm exercising a lot, and I'm constantly burning calories. My wife picks on me. I've been picked on my entire life for being so thin. I can't change it, though. At any rate, what I'm meaning by this symmetric conjugate symmetry, it's showing up here in the last two bullets, but conjugate symmetric with respect to what? So we can either think of the Fourier transform, we know it's periodic, so how do we want to think of the periodicity? On the interval minus to plus pi is one way of thinking of it. The other way of thinking of it is from 0 to 2 pi. So what are the symmetric or conjugate symmetric intervals? They're taken in either of these two forms. So I always forget I can walk around because I've got the wireless on. I like thinking of it in here more readily because if I'm plotting in Python, I'll generally start at 0. But so this is the interval, and this is a conjugate symmetric interval. If it's up above, the interval is 0 to pi, and then the conjugate symmetrical is minus pi to 0. Does that make sense? This, like I said, is the easier one to do, or the easier in my mind. It also relates really well to the fast Fourier transform in DFT later on. Just depends on how you want to think of it. But if I'm thinking of radio signals, which is what I work in, what's called complex baseband, we actually saw earlier that if I have a complex signal, and we could have a sinusoid right in here, it's not going to have an image at the negative side. It's not going to be conjugate symmetric. That's for a complex signal. And that's what radio signals are. Hey, I'm going to show you something that I feel like I should show you because it's something that actually came up in my meeting today, but not from me. It came up. This was a project from last year. It was called a channelizer. And so the way you can think of a radio signal in this particular example, we're going to channelize the AM broadcast band. And I guess it's slow to updating here. Here's what I'm looking for. So in this particular picture, instead of thinking of 0 as being 0 hertz and being conjugate symmetrical about 0 hertz, what we're going to do is see the radio signal. AM broadcast band runs from, does anybody listen to AM, by the way? Ever?
AM, no, FM.
Yeah. Do you know what AM is used for today?
Not really.
Okay. Talk radio, primarily, is what I think of it, and sports. If you want to drive from here all the way into Kansas and listen to a Rockies game or a football game, you could tune in AM radio and you can listen to it if it's on a clear channel a long ways away. FM eventually goes away because it doesn't cover the same electromagnetically as lower frequencies do. At any rate, in this case, AM radio runs from 470 to 1670 kilohertz, and the center of that band is 1070. So what we're going to do in this project with the channelizer is we're going to take and digitize with a software-defined radio, set the center frequency at 1070. So when the signals come in through this channelizer, which is consisting of 5 bands and then 5 bands of 24 each to channelize down to the individual band that the signal exists in, we're going to make 0 become 1070 hertz. And it's going to be a complex spectrum then. complex signal. Everything across the band will be channelized down. And the channelizer, what I mean by that is if you process a band of signals where there's like 10 signals in that band, how do we separate them? We have to filter them down. So what we're going to do with the channelizer is we're going to be like a comb going through that AM band, and each output is like a tooth on a comb. It's going to have just one signal in it all by itself. Sound crazy or not? An advantage of the channelizer would be that you could listen to all of them simultaneously, whereas normally in a simple radio like FM, AM radio, you will tune with a super heterodyne technique, which you learn about in COM 1. You'll just zoom in one frequency, but you'll ignore everything. So with the channelizer, if you're a surveillance radio, you could be monitoring all these channels simultaneously. Does anybody care to do this? Yes, right? I mean, people do want to monitor, do surveillance. So that wasn't, my motivation was just building something that was kind of cool. So what happens in the end in this project, and I'm getting kind of tired of looking at this part of it since it's kind of maybe more than I want to show. I'm going to go look at the PDF rendering in the notebook because I cut to the chase a little bit faster. There it is. Right there, actually. That's it. So there's another zooming of it, but in this case, this is the 5 bands of the channelizer, and you can see there's multiple signals in some of those bands, right? These end up being weak signals that were too far away to actually demodulate, but this band has 2 in it, and I think this has 2 in it, but they're clustered together. So then we channelize again, and now we'll be able to get it down. So this is what the pass bands look like across one of the subbands, and then this is what one of the subbands looks like when you finally channelize it down. So that way you can just take the signal that's coming out of this guy and demodulate it, get the information from it in this one too, in parallel, rather than just tuning one at a time. And that's what this project has you play around with, assuming I go with it again. I spent a fair amount of time creating it, but I got excited about just starting this TV because when I was talking about symmetrical, I'm sidetracked. But real signals will always be DC is DC, and what's up above is the symmetrical version of what's below. Always, 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 always. But in RF and in complex signals, then when you represent a complex signal at so-called baseband, you center it at DC, but now it's unique across that entire band. But lest I'm getting you confused, which I may be, this says real signals, so it's a much simpler case. It may never be of interest to you to do anything but real signals. If you did audio, fine. For me, doing communications, complex signals are the norm, pretty much. At any rate, the important properties for a real signal is conjugate symmetric, and if it's conjugate symmetric, it means that the magnitude is even. So if we're centering it on 0, it's even, and the phase is odd. But we can take that same idea of even and odd and break it so that when we're doing it like this, what's sitting right here is actually now right here because it's periodic, right? I can just slide this over and I can put a 2 pi band anywhere. So this is down is here. So that and that are phase is odd and magnitude is even. So that I want you to know and take advantage of that. So generally when we're plotting the spectra of a real signal or plotting the frequency response of a real impulse response, what I want you to do is not waste paper in a sense. I want you to just show this band. Just want you to zoom in on the uniqueness of it because it's conjugate symmetrical. So the unique information is all in half the band. And if we have an even signal x of n, then the imaginary part is 0. And then the next step of that is if it's an odd signal, then the real part is 0 and everything's in the imaginary part. These are all things from Fourier transforms from 3205. I don't know if you remember it or not, but pointing it out here. And this is from the book. This is why I'm not going through symmetry properties. What I just told you is all I mostly care about. This is like the kitchen sink. I mean, this is like everything, all kinds of interesting properties here. The real case is considered in here, but it's got more than just that. So now we'll go and look at something that was in the Jupyter notebook and something I alluded to last week. Let's just delve into Fourier transform calculation, and then we'll delve into the theorems. So suppose we want to get the Fourier transform of this kind of classical signal I was talking about already tonight, the a to the n u of n, which remember well, I'm not trying to draw it as a signal, a system, I mean. Never mind, I'm not going to do that. Just a to the n u of n. So go ahead and get the Fourier transform by putting the signal in the definition. The definition will now just sum from 0 to infinity because the signal is 0 for n less than 0. We have a to the n, and then we multiply by e to the minus j omega n. So there's a dot in there, I guess, because the e to the minus j omega n is the weighting function that goes with the definition of the Fourier transform. But then factor out the n in the exponent, so we get a times e to the minus j omega in parentheses there, and we have raised to the power of n, and our lights go off and says geometric series once again. It sums up to 1 over 1 minus a e to the minus j omega. And for this to be summable, absolutely summable, we already know that the magnitude of a e to the minus j omega just has to be less than 1. And since the magnitude of e to the minus j omega is 1, it just says magnitude of a has to be less than 1. So this is a convergent sequence. I mean, it's a absolutely summable sequence. So it's Fourier transform exists as long as magnitude of a is less than 1. And we could say if we were talking about an impulse response rather than just a signal, then we just say stable if magnitude of a is less than 1. And we've already seen that already. If you wanted to go on to demonstrate the symmetry conditions I just went through, we could make the denominator real by multiplying by its conjugate, top and bottom, and then we'll get this x of e to the j omega, which can be broken apart into real and imaginary parts, because we know that if we multiply the denominator by its conjugate, what happens? It's now just a real number, right? So we can factor that out and just leave it alone. It's a real part, I mean, it's real, so that's this guy right here. You know that's the case, right? And I know that's the case, because you'd say, wait a minute, there's a j in here, but what is that? That's just a cosine, right? So we're good. We didn't cheat or didn't brush anything out of the way unknowingly. So now we can break it apart into the sines and cosines and magnitude and phase. So these additional writings here just let us see that, yep, the real part is even, imaginary part is odd, magnitude is even, and phase is odd. Now, just as a check on memory and other things, how can I just say even and odd so quickly? What are things that you know about the composition of this stuff? Cosine and sine is what I'm keying off of. I guess maybe arctangent, but cosine and sine. Sine is an odd function, right? And cosine is an even function. So this is even because it's just got cosine in it. This is even, it only has cosine in it. This is odd because it has that sine with the even, and this is odd because it hasn't the sine in it.
What does that mean, that it's even? Does that mean that I got 0?
I can take omega and make it be positive and go negative, and it gets the same functional value.
Okay.
That's all I'm meaning. And that's what the pictures here show. I feel like this is kind of, in a sense, silly, but I don't think about this as much anymore since I've been using the computer to do these calculations for such a long time. I think in the beginning, people wanted you to get all warm and close with all these functional forms and saying, it's great because of these symmetry properties, we don't have to worry about calculating negative values because of symmetry and so on. But nowadays, if you're drawing a picture of something, or if I say draw a picture in your homework solution, you'll gladly just let the computer draw it for you, right? In the beginning, though, we didn't do that because it was work to do that. As a matter of fact, it just didn't get done. You would draw a hand sketch, right? And you, for drawing a hand sketch, you draw some axes, and then you draw a couple points, and then say, okay, these points are the same on the other side, and so on and so forth. Now, in an exam, exam 1, you will have to do that maybe, so these things can be useful for that. So let's go into the theorems. This is the fun part because it will allow you to work the homework problems faster, and it will allow you to get them done. So we have the transform theorems. The notation the book likes to use is the script F for Fourier and a waveform, a signal or sequence x of n transforms to x of e to the j omega, assuming it exists. And these theorems, we assume they exist. And then script F to the -1 means it's the inverse Fourier transform. And then a pair is got x and capital X next to each other with a double-ended arrow with the F over the top, just meaning it's a transform pair. Transform pairs, open this up already, so remember we have this second page of the cheat sheet that you'll have for the exam. So I'm thinking of that right now because I'm thinking of having that open when I'm working problems to make sure I can leverage it. So linearity is an obvious problem, an obvious property because of the fact that we're involving a sum, or an integral in this case is just a sum. So the Fourier transform is the sum with the e to the minus j omega and weighting, and linearity holds. So we can individually transform and gain scale and move things around. So that's a really nice property. The time shift theorem is very nice to take advantage of. I said we'd be getting to that towards the end tonight. So you take a sequence and shift it by some ND, positive or negative, whatever, and you can just have that ND creates the e to the minus j omega nd. And remember, that was the Fourier transform of a delta n minus nd. Remember, all by itself, it was just that alone. And you can get that proven by just substituting into the Fourier transform theorem. So if you're thinking about how it would happen, you'd just be making a substitution in there directly. Actually, you'd be turning this around. If you were doing it as a proof, you would, I guess, have to do a little better job on it, because I may give you a theorem to show or prove in the exam. It's a really good possibility, actually, on exam 1. So if you were going to do this, what you would do is you would come down from here, and you would start off by saying, okay, I'm going to plug in x of n. And rather than writing out the limits, I'm just going to put n down below there. And that, what would be the next step you would do if you were going to make a proof of this? I would probably say let m equal n minus nd. Okay? Does that sound reasonable? You want to get the n reduced down to the definition, so you'd have x of m. And then you have to replace, under this change of variables, you have to replace n by its new value, which is going to be, from this substitution, it's going to be m plus nd. So now you can just factor out in front of that sum e to the minus j omega nd, and that's the proof right there, right? You're just one additional step away from getting there. And this second theorem is the same way. It's a similar type argument. I do sketch through the proof a little bit there. Good. I mean, it's not super hard, but it's just useful. I mean, the observations that you make along the way, and say, I'm not going to have to prove that again because I've already worked it through. I know it works. So the delay theorem is powerful. It's used in the homework problems, and I've got an example coming up. That's kind of where I'm heading to close out the night, to that point. Frequency shift is really good too, because we're working with modulating a waveform. We're getting into a communications theory idea about a waveform. It just says we can take a signal x of n and we multiply it by e to the j omega naught, and we'll be shifting its spectrum up to a new frequency location. So I think I didn't draw a picture of that in here, but as a result of applying that theorem, it just shifts it in one direction. It shifts it up by plus omega naught. And that's useful in shifting the spectra of signals around. It's actually that channelizing radio makes use of that property a lot. In digital or analog and digital communications, and DSP make use of this property a lot. You just create a waveform. You have a waveform, and then if you want to transmit it, you can shift it up in frequency, and then you can convert it. You can do the conversion back to analog, some different locations in the processing. And there's a proof. Parseval's theorem is just in here for completeness, saying that the energy in the frequency domain side is equivalent to the energy in the time domain side. The proof of this one is a little bit more detailed, and it just involves the definitions again. This theorem is very, very useful, the convolution theorem, and it's pivotal in most anything you do with Fourier analysis, but most of the time in the class we don't always use the Fourier transform for the convolution theorem. We end up using the Z transform more often, but we can, at this point in the course, we can use it as our only transform domain technique to get there. We'll have the options after chapter 3 of using it, doing the Z domain if we want to, but convolution, the sequence domain becomes multiplication in the frequency domain. So this gets used in the homework problems as well, definitely. And the proof of it is not a rigorous proof, it's just interchanging orders and then proving that it's true from these steps. This theorem is useful if you're wanting to understand windowing theory, in particular in filter design or in spectral analysis. So I have an example built around this, and the windowing idea is this. It's like if we want to take a signal X of n and we want to shape it with a window so that it's more controlled, or if X of n was the impulse response, we want to window it, like in the sine sinc X impulse response earlier tonight. We could shape it to get the side lobes down better. That's where the windowing theorem comes in. And I have an example of that later. I may not decide to drill into it tonight because it's not important for the homework coming up. I do want to get far enough along. But the proof of it's down here, and I'll explain it more if we do go through the example. I'm not positive which I want to do because I want to spend time on some homework. So I just pasted in some of the tables in here that are useful, the same things that are in the website. So 2 more examples. Just how can we use theorems to do Fourier transforms? This is a kind of a simple one, but it just shows you how you can leverage the power of the theorems, and this is going to leverage the power of the delay theorem. So you have X of n is a to the n, U of n minus 5. You say, how do I get the Fourier transform of X of n? You could just work directly with a definition, but if we were shrewd and wanted to use the the delay theorem, we can bring an a to the 5 out in front and then keep n minus 5s grouped together so that we can apply the delay theorem. In other words, to apply the delay theorem to what's in parentheses, we have to take advantage of the fact that we have n minus something everywhere inside there. So we arranged it to get n minus 5, and then we can just get the delay theorem will just be the Fourier transform of the undelayed a to the n U of n, and then this gets brought in from the delay theorem. And then the a to the 5, which was brought outside, just carries over because it was necessary to apply the delay theorem. And once this gets put together, you can get the Fourier transform of a to the n U of n, which is 1 over 1 minus a to the minus j omega. Bring that out from the tables, or just recompute it, and then you just add the 2 pieces on top of it right here that came from the application of the theorem. Good? Example of using the windowing theorem, which I'm going to not necessarily finish on tonight. I'm going to move on to the next example. This is mentioned in the hints page for working the homework problems. This is key, pivotal to working any of the problems where you would like to solve the difference equations using the Fourier approach rather than the classical solution technique. So if you're given a difference equation, this is a first order difference equation. It could be second order, the problem's in the notes. You take and apply the delay theorem to all the terms in this difference equation using the Fourier transform. So you Fourier transform both sides sort of in a, what's the right word, in an operational sense. Y of n becomes y of e to the j omega. 1/2 y of n minus 1 becomes 1/2 e to the minus j omega from the one sample delay times y of e to the j omega, so on and so forth. As soon as you get this set up, then you jump into the convolution theorem, which says y of e to the j omega, we know, is just x of e to the j omega times h of e to the j omega. So we factor the y of e j omega is out on the left-hand side, and the x of e to the j omega is out on the right-hand side. And then we form the ratio of y over x, and we're left with, the numerator term from the factoring on the x side and the denominator term from the y side. And this right away shows you how freak Z was set up to work, because it had a numerator and denominator, and it was assuming you had a general difference equation that you were going after to get its frequency response. Does that make sense? How that comes together. This is beautiful. It's like easy, easy, easy. You just have to know how to put it together and get it to work. And you don't have to go forward with it. You can take it backwards. You can go backwards and forwards with it, and it's useful any which way you want to use it like that. So in some cases you'll go forward with it. Other cases you want to go backwards. So suppose you want to go backwards and you already had h of e to the j omega given to you. How are you going to get back to the impulse response? Well, we know all we need. Well, we could get back to the difference equation, of course, by stepping all the way backwards and getting back to the difference equation at the beginning. But suppose instead we wanted to go backwards to get the impulse response, then we know we just need the inverse Fourier transform, okay? So we just look at this and say, how are we going to do that? Well, we have to think in terms of partial fractions. We have to think in terms of really this basic A of n, U of n is kind of the thing that we're driving for. We're saying if we get that all by itself, we know it's a to the n u of n. If it gets dressed up on the top with a 1/4 e to the minus j omega, that just came from a shift of one sample and a scale factor of 1/4. So we can put it back together in fairly short order to get the impulse response. In the homework problems, when you get to use this, and I hint at it in the hints, you get to do a little bit of partial fraction expanding, but it's not very hard to solve for the coefficients. And you've seen partial fraction expansion before, so you're just going to be solving for two coefficients where you have two different denominators, and you'll just be able to then decompose it in using this technique. Sound reasonable? Follow my hint. I'm not making you cheat. I'm just saying be smart about it. And I want you to be smart from the very beginning. I think it's silly to wander off in the dust and then get lost and not get pointed in the right direction, because it's there for a reason. And this example was definitely included for a reason. It was so you could leverage it, and leverage it you will. I'm convinced, based on grading the homework. I know that I gave you hints before, and I'm seeing how you're working on it's worked, right? Maybe not perfect, and you'll get your papers back and you see where I nitpicked at things, but this will help you a lot. So thinking of the couple minutes that are left, brought my tablet in here for a reason, so I'm looking at, let's go back over to the web browser, the homework. So in the homework, the first two problems are, which problem is it? Problem 2.9. It says you want to get the step response. So if you solve by the classical solution technique for difference equations, you would drive it with u of n, and then you would solve for the particular solution with the u of n driving function. That would come out as a separate solution using the classical solution technique. If you elect to go with the Fourier transform method, you will, see if I can get this thing shifted into the right gear, you will instead get this, and then how are you going to get the step response? How are you going to go do that? You have to take another route to get there, and this is the technique that you use. You know that if you have a linear time invariant system, and if you use linearity on it, you can convolve the step function with the impulse response, and that gives you the step response. So what does that mean over in the time domain side when you're trying to manage the action of the step function in the convolution? It just says you're just going to accumulate the impulse response from 0 up to infinity, or up to n, and then that will give you the step response. So you say, how am I going to do that? Well, when you plug that in and wrap that sum around it, you're going to see that to get those sums is just another geometric series, which you can do because you've done it before. So you can get at it that way. And what I recommend you do, and what I did in my solutions, I'm just looking at right now, is I took the step response and I went ahead and evaluated it in Python, because you can go check some of the points out if you want to. You could evaluate a few points. I did both. I did all the solution techniques in my solutions because I wanted to just cover my bases. But you can check in a numerical solution in Python if you want to the step response and just see if that makes sense or not from the difference equation. Because from the original difference equation, you can do a recursion, right? When we talked about that last week, you just start out at n is equal to 0, assume the initial conditions are 0, put a step in at the input, see what the output is at n is equal to 0, and then bootstrap up to n is equal to 1, 2, and 3, and then you can take your closed form solution you get out over here and just evaluate it, n is equal to 0, 1, 2, and 3, and see does it match what you got by recursion to see if what you did in the geometric series was legit or not. Does that sound cool? I mean, I want you to be self-checking at all times. A systems engineer like me in industry, I'm always self-checking because I have to make sure I don't mess something up, because I move on to give somebody else some more work to do, and if I tell them the wrong thing, then I'm in bad shape. I do make mistakes, so we all make mistakes, but at least you stay on top of it and say, whoops, I didn't do that right. I checked it later and it wasn't right. I made a mistake. Here's the work again. So get in the habit of being that way, though, because being rigorous about stuff saves you embarrassment, one, but saves you from just sending somebody, a teammate, in the wrong direction. And I'm trying to think, I may have done that recently, but I don't know. I'm a crazy person, and you probably are crazy too. When you're in the middle of the night or you wake up in the morning. Yesterday I was walking my dogs. I was thinking, or someday this weekend, about testing with some data we had taken last week on my project. And I said, I don't have to ask somebody to take some more data. I have this column in the data table from the measurements we made and captured, a log file. And I said, I can test this Monday morning to prove that something was wrong in a numerical calculation. And sure enough, it was wrong, and today it was tested again, and he fixed it, and it works. It's like, but I didn't think of that last Friday when I was upset about something not working. I had enough data that I could do it on my own to get a head start to convince somebody else that, hey, look at this. Oh, yeah, let's look at this. I see a problem here. And then it got fixed. So that's teamwork again, too. But I had added confidence because I proved to myself, and I was not going to let down. And he agreed with me. So what else can I do to help you right now? I will come here early next Tuesday. If there's any office hours, remember the policy will be in effect that you can turn your homework in after class if you want to. Play Audio Helper is not needed right now, but again, I'll just reiterate, look at the very first project problem if you're bored and want some more homework to do. You can look at the Z-transform because we'll be discussing that. That chapter is probably the most fun chapter of the entire semester. It's very, I'd say, easy peasy to get through the next chapter. So we're finishing off one of the more challenging parts, and it's still not too bad, but go look at that programming task, and we'll talk about it maybe next week if you've gotten started on it, or message me on it if you want to. Are you going to retract your homework and retweak it? Don't just do it if you want to. If you got an idea to make it cleaner,
Yeah, I think.
just look at it again, because that way I'll save you some grief of having to, if you think there's something you want to look at.
Yeah, I think most of it I just taught myself.
You can take it back, though. You can right-click it in Slack to host for the other two. If you send something and you say, I wish I didn't send that, it's wrong, just immediately, you were the author, you pushed it onto Slack, you can remove it from Slack and just delete it, get it cleared away, because if it lingers around, I'm apt to be confused and not know which one to grab. I get confused, but you can retract it pretty much.
I'll check and I'll delete it if I think I did anything wrong.
Yeah, don't hesitate, because careless errors are so easy to make. I mean, I've seen them in the grading so far, and I may ding you a point here or there because I'm just saying I want you to understand it, and I realize maybe you didn't intend to do it, but maybe you just didn't want to work the extra mile. So I'm making you recognize that fact.
Yep.
And we're all in this together, so it's good.
Okay.
I'm feeling a whole lot better. I'm going to have to eat a Cliff Bar every week, I think, to keep myself alive.
Yeah.
Okay. Have a good night.